day, students. Today we shall learn how to study interference of light using mathematical equations. Now, why do we need it? In order to study any phenomenon or any system around us, we first need to describe it. And we try to describe it in terms of any relation or in terms of any equation. Okay. And if we can satisfactorily explain it using the mathematical equation, we can control that phenomenon or we can modulate that phenomenon according to our variables. Okay. Now, in interference of light, we should consider the simplest case, the superposition of two waves. Okay, so here we are going to see what happens when two waves are allowed to superimpose, two light waves are allowed to superimpose upon each other. Now first, let us see what do you mean by the phase difference in a wave and the path difference in a wave. Here we have two waves. The blue wave represents a sine wave and its initial position is at the phase value 0, right? The maroon colored wave is preceding the sine wave by a phase of pi by 2, right? So the maroon colored wave can be represented as sine of omega t minus pi by 2. Okay, so what is sine of omega t minus pi by 2? It is cos omega t. Thus, the maroon colored wave represents a cos function. Okay, now these two waves do not have the exact same initial positions, right? So this difference is usually represented as the difference in the phase is called the phase difference, and the difference in the paths between the rays is called its path difference. Okay, so phase difference delta is the difference in the phase angle of the two waves, and the path difference is the difference in the path traversed by the waves. The relation between phase difference delta and path difference are direct. They are directly proportional to each other. Mathematically, it is given as phase difference delta is equal to factor 2 pi by lambda times path difference. Inverse relation can be obtained as path difference is equal to factor lambda by 2 pi times phase difference delta. Now let us look into the intensity distribution of the interference pattern due to two light waves. So let us consider two waves that are having a finite phase difference between them. So the first wave can be represented as EA is equal to E1 sine of kx minus omega t. From this we understand that the direction of propagation is in the positive x-axis. Okay. Now the second wave can be represented as EB is equal to E2 sine of kx minus omega t plus delta. Here delta represents the phase difference between these two waves. When these two waves superimpose upon each other, they follow the principle of superposition to give the resultant wave as ER is equal to EA plus EB. This becomes ER is equal to E1 sine of kx minus omega t plus E2 sine of kx minus omega t plus delta. Kindly follow through this derivation with your notes. Okay. Now, in the sine kx minus omega t plus delta term, here I can consider this as sine A plus B, where A is kx minus omega t and B is delta. So expanding it, I should write sine A cos B plus cos A sine B. Hence, we get the next step, E1 sine kx minus omega t plus the expanded term E2 times sine kx minus omega t cos delta plus E2 times cos kx minus omega t sine delta, right? Now, the sine kx minus omega t terms can be clubbed together. So we get sine kx minus omega t into E1 plus E2 cos delta plus the remaining term cos kx minus omega t E2 sine delta. Here, we are going to substitute for two terms. E1 plus E2 cos delta is being substituted as E cos phi, and E2 sine delta is being substituted as E sine phi. Thus we get E cos phi sine of kx minus omega t plus E sine phi cos kx minus omega t. Here, taking E as the common factor, we get sin A cos B plus cos A sin B term, again which can be reduced to E sine of kx minus omega t plus phi. Thus, we get the expression for amplitude of the resultant wave as ER is equal to E sine of kx minus omega t plus phi. Here, E is the instantaneous amplitude and phi is the phase difference. Let this equation be numbered 1. Here, the substitutions are E1 plus E2 cos delta is equal to E cos phi. This is equation 2, and E2 sine delta is equal to E sine phi. This is equation 3. Now, from these two equations, 2 and 3, we can calculate the value of E and phi. So, squaring and adding the second and third equations, we get E1 plus E2 cos delta whole square plus E2 sine delta square is equal to E cos phi square plus E sine phi square. This gives, on expansion, we get E1 square plus E2 square cos square delta plus 2E1 E2 cos delta plus E2 square sine square delta is equal to E square into cos square phi plus sine square phi. Okay, thus we can write E1 square plus E2 square plus 2E1 cos delta equals to E square. Here we have taken the substitution sine square theta plus cos square theta is equal to 1. Thus the expression E square is equal to E1 square plus E2 square plus 2E1 E2 cos delta is obtained, and this is the fourth equation. The phase of the wave can be calculated from dividing the third equation by the second equation. Hence we get E sine phi by E cos phi is equal to E2 sine delta by E1 plus E2 cos delta. That is, tan phi is equal to E2 sine delta divided by E1 plus E2 cos delta. Therefore, phi is equal to tan inverse of E2 sine delta divided by E1 plus E2 cos delta. This is your fifth equation. Thus, the intensity distribution of the interference pattern due to two light waves can be summed up as ER is equal to E sine of kx minus omega t plus phi, where you get the amplitude E square is equal to E1 square plus E2 square plus 2E1 E2 cos delta, and the phase phi is equal to tan inverse E2 sine delta divided by E1 plus E2 cos delta. In the expression for amplitude, here the first term represents the instantaneous amplitude of the first wave. Second term represents the instantaneous amplitude of the second wave, and it is the third term that represents the interference term. In nature, we cannot observe the amplitudes of light waves. We can only see its intensity. Hence, using the terms of intensity, we have the relation I is equal to half of epsilon naught E square. It implies that the intensity is proportional to amplitude E square. Thus, we get the expression for intensity as, substituting for I wherever there is E square, we get I is equal to I1 plus I2 plus 2 root of I1 I2 cos delta. Here I1 represents the intensity of the first wave, I2 represents the intensity of the second wave, and 2 root I1 I2 cos delta represents the interference term. Now, when we use coherent waves for this interference, the amplitudes of the waves will be almost equal. So we can take the approximation that E1 is equal to E2 is equal to E0. Thus, the expression becomes amplitude E square is equal to E naught square plus E naught square plus 2 times E naught into E naught cos delta. Here, taking E naught square together, we can write 2 E naught square plus 2 E naught square cos delta, that is 2 E naught square into 1 plus cos delta. Here 1 plus cos delta is substituted as 2 times cos square delta by 2. So you get E square is equal to 2 times E naught square 2 cos square delta by 2, that is E square is equal to 4 E naught square cos square delta by 2. And this is your sixth equation. In terms of intensity, this expression becomes I is equal to 4 I naught cos square delta by 2. This is your seventh equation. Now we are going to consider two cases where the values of the phase difference gives meaning. In the case 1, let the phase difference delta be an even integral multiple of pi, that is 2n times pi. The expression for amplitude becomes E square is equal to 4 E naught square cos square 2n pi by 2. Here cos square n pi, its value is 1. Substituting values for n as 0, 1, 2, 3, etc., we always get that cos square n pi is equal to 1. Hence, E square is equal to 4 E naught square. In terms of intensity, I is equal to I max is equal to 4 I naught. This is the maximum possible value for the light intensity. In terms of path difference, we can write it as the factor lambda by 2 pi into phase difference. That is lambda by 2 pi into 2n pi. This implies that path difference is n lambda. That is, when path difference is an integral multiple of lambda, we observe constructive interference of light, where the intensity is maximum. Now, in the second case, where the phase difference delta is an odd integral multiple of pi, the expression for amplitude can be written as E square is equal to 4 E naught square cos square 2n plus 1 pi by 2. Here, cos square of 2n plus 1 pi is 0. You can verify it by giving values of n equals 1, 2, 3, etc. So this implies E square is equal to 0. In terms of intensity, I is equal to I minimum is equal to 0. This is the least possible value for the intensity of light. In terms of path difference, this can be written as lambda by 2 pi into delta, that is lambda by 2 pi into 2n plus 1 pi. This gives that the path difference is an odd integral multiple of half wavelength when the light intensity is minimum. So if the interfering waves have a path difference of odd integral multiple of half wavelength, we get destructive interference, where the light intensity is minimum. Now, let us try to find out what is the exact distribution of this expression of intensity. So for that, let us first draw a table. And in this table, we have to have 4 columns. First column represents the delta phase difference value. Second column represents delta by 2 value. Third column represents cos square delta by 2. And the fourth column represents intensity I value. And for each values of phase difference, we are going to find the values of intensities. Now to calculate the phase difference, I have given the reference value of cosine curve on the right side. First, let us consider what happens when phase difference is 0. Here, delta by 2 is 0. Cos square delta by 2 gives cos square 0 gives 1. Hence, intensity is 4 I naught. Now, when the phase difference is plus or minus pi, delta by 2 becomes plus or minus pi by 2. Then the term cos square plus or minus pi by 2 becomes 0, right? Hence, the expression for intensity becomes 0. I need you to tabulate the column for phase difference values of plus or minus 2 pi, plus or minus 3 pi, plus or minus 4 pi, and plus or minus 5 pi. Try to calculate it, pause the video, do the mathematics, and after that you can continue watching. Now, when phase difference delta is plus or minus 2 pi, delta by 2 gives plus or minus pi. That implies cos square delta by 2, that is cos square of plus or minus pi is 1. Hence, intensity becomes 4 I naught. Again, when delta is plus or minus 3 pi, delta by 2 is plus or minus 3 pi by 2. Cos square delta by 2 is 0, hence intensity is 0. Now, when your phase difference is plus or minus 4 pi, delta by 2 is plus or minus 2 pi, cos square delta by 2 is 1, hence intensity is 4 I naught. And when delta is plus or minus 5 pi, delta by 2 is plus or minus 5 pi by 2, and the cos square delta by 2 is 0, hence intensity is 0. Now let us represent this in an intensity distribution curve. For that, we are going to plot the phase difference in the x-axis and intensities in the y-axis like this. So in the x positive and negative axis, we have phase difference values, and on the positive y-axis, we have the intensity. Now, when delta is 0, the intensity is 4 I naught, and let us represent it at this point. When delta is plus or minus pi, the intensities are 0. Let us represent it at these points. Now, when delta is plus or minus 2 pi, I is 4 I naught. So let us represent it at these 2 points. Okay. Now, when delta is plus or minus 3 pi, intensity is 0. Hence, we plot it at these 2 points. Okay. Now, when phase difference delta is plus or minus 4 pi, the intensity is 4 I naught. So we get these 2 points. And at plus or minus 5 pi, the intensities are 0. Now, if we plot a line passing through all these points in a continuous manner, we get a pattern like this. Here we can see that alternate maximas and minimas are distributed, right? and these maximums and minimas are equidistant from each other too. So this is the nature of the curve that we obtain by the interference due to two light waves. Does it match with what we see in reality? Here, this is an example for the interference of light due to two light waves. And here again, we see that we have alternate bright and dark regions having equal widths that are equidistant from each other, right? The bright points are equidistant from each other, and the dark points are also equidistant from each other. You view this as a spot because we have used a light ray, a laser source for this interference, and hence we observe the pattern on a small region, on a small spot. If our source is broadened, this interference pattern will be spread over the whole screen. Okay, so we have succeeded in mathematically representing a natural phenomenon. Okay, so the expression I is equal to 4I naught cos square delta by 2 can successfully explain interference of light due to two light waves. Hope you have understood this session. Thank you.